Right now, as you're watching this video, something truly extraordinary is happening in our solar system. An object older than Earth itself, possibly more ancient than our Sun, is racing toward us from the depths of space. And here's the wild part. We're watching it arrive in real time. This isn't the first time we've had unexpected visitors from beyond our cosmic neighborhood. In fact, what started as a once-in-a-lifetime astronomical event has suddenly become a recurring phenomenon. And each new arrival brings with it more questions than answers. What are these objects? Where are they coming from? And perhaps most importantly, are they really just rocks? Let's dive into one of the most fascinating mysteries in modern astronomy. Our story begins in October 2017, when astronomers at the Pan-STARRS telescope in Hawaii were doing routine observations. They spotted what they initially dismissed as just another space rock, probably a comet making its regular loop around the sun. But within days, something became clear. This was no ordinary celestial body. The object had already completed its closest pass by the sun and was accelerating away from our solar system at breakneck speed. By the time we realized what we were looking at, it was essentially saying goodbye. The Hawaiian astronomers gave it a name that perfectly captured the moment: Oumuamua. In their language, it means a messenger from afar arriving first, or more simply, the scout. Because that's exactly what it was. Our first confirmed visitor from another star system. Think about that for a moment. This object began its journey millions of years ago, traveling through the absolute emptiness of interstellar space. No light from any nearby star, no gravitational influences, just silent, frozen drift through the cosmic void. And then, after eons of solitude, it encountered us. Now here's where things get interesting. Everything in our solar system exists within the sun's gravitational dominion. The planets, asteroids, comets, we're all perpetually bound by this immense force, orbiting in our designated paths like boats circling a massive drain. Breaking free from this gravitational grip requires achieving what physicists call escape velocity. From Earth's orbital position, you'd need to be traveling at roughly 42 kilometers per second to break free. That's about 150,000 kilometers per hour, fast enough to circle the Earth's equator in under 3 minutes. When we measured Oumuamua's speed as it crossed Earth's orbital path, it was moving at 87 kilometers per second, more than twice escape velocity. The sun's gravity had absolutely no chance of capturing it. But wait, it gets weirder. Before reaching our vicinity, Oumuamua had ventured deep into the solar system, passing even closer to the sun than Mercury, the innermost planet. When you fall that deep into a gravity well, physics dictates that climbing back out should slow you down. It's like rolling a ball up a hill. Gravity fights against you every centimeter of the way. Oumuamua didn't slow down, it sped up. Something was pushing it. Something from within the object itself was generating force, acting like an engine accelerating it out of our solar system. And that's physically impossible for an inert rock. If Oumuamua's motion was puzzling, its appearance was downright bizarre. When astronomers analyzed the light reflecting off the object, they noticed something unusual. It wasn't steady. The brightness fluctuated dramatically in a regular pattern, cycling from bright to dim every 7 hours. This told them something crucial about its shape. Spherical objects, like most asteroids, reflect light consistently as they rotate. But Oumuamua's dramatic brightness variations suggested we were seeing something elongated, watching it tumble end over end through space. The calculations suggested an extreme shape. roughly 10 times longer than it was wide, like a cosmic cigar, or, as some pointed out, like a disc or saucer viewed edge-on, spinning as it traveled. And here's another oddity. Oumuamua was remarkably bright and reflective. Most asteroids are dark, rough rocks that absorb more light than they reflect. But this object gleamed. Whatever it was made of, it wasn't typical asteroid material. So we've established that Oumuamua was accelerating without any visible means of propulsion. But actually, there's a perfectly natural phenomenon that does exactly this. Comets. Comets are essentially dirty snowballs from the outer reaches of our solar system. The Oort cloud, a vast spherical shell of icy debris surrounding our planetary system. When one of these frozen wanderers falls toward the sun, solar heat causes the ice to sublimate, transforming directly from solid to gas without melting into liquid first. This outgassing creates the beautiful glowing coma and streaming tail that comets are famous for. But it also acts as a natural propulsion system. Gas jets shooting off the sun-facing side create thrust, like tiny rocket engines firing, which can measurably alter the comet's trajectory and speed. So if Oumuamua was accelerating, couldn't it just be a comet? Problem solved, right? Not quite. Because Oumuamua showed absolutely zero signs of being a comet. No fuzzy coma surrounding it, no tail streaming behind it, no detectable outgassing whatsoever. Every telescope we pointed at it saw the same thing, a solid, tumbling object with no visible activity. Yet it was accelerating exactly like a comet would. It was behaving like something with active propulsion, but looking like an inert rock. And that combination doesn't make sense in our understanding of natural objects. Let's talk about where this mysterious visitor came from. When astronomers backtracked Oumuamua's trajectory, they found it pointing toward Vega, one of the brightest stars visible from Earth, and a cornerstone of the constellation Lyra. Vega isn't just any star. It's been a landmark in human navigation for millennia. Around 12,000 BCE, Vega actually served as Earth's North Star, that fixed point in the sky that ancient mariners used to navigate. Due to Earth's axial precession, our planet's slow wobble as it spins, the North Star changes over time. Right now it's Polaris, but in about 12,000 years, Vega will reclaim that role. Now, Oumuamua didn't necessarily originate from the Vega system itself. It just came from that general direction. But there's a cosmic coincidence here. That's also the direction our entire solar system is currently heading as we orbit the galactic center. So in a sense, we and Oumuamua were on a collision course. We didn't just observe it passing through, we actively intercepted it. As Oumuamua curved around the sun, its trajectory brought it toward Earth. At closest approach, it passed within 24 million kilometers of our planet. Now, in astronomical terms, that's quite close, only about 60 times the distance to the moon. But it's still far enough that if this were some kind of probe, it would need sophisticated instruments to observe us. We first spotted it just a few days after this closest approach, when it was already racing away from us. We'd missed our best opportunity to study it up close. Naturally, scientists proposed sending a spacecraft to chase down Oumuamua and study it directly. But the hard reality is that it's simply moving too fast. It had too much of a head start, and no conventional rocket propulsion system we currently possess could catch up to it. Theoretical mission plans involved incredibly complex maneuvers, sending a probe to Jupiter for a gravity assist, falling deep toward the sun, then using the sun's gravity as a slingshot to fling the spacecraft toward Oumuamua's trajectory. Even then, success would be uncertain. If Oumuamua had been a singular anomaly, the only interstellar object we'd ever encounter, such an ambitious and expensive mission might have been justified. But as it turns out, Oumuamua was just the beginning. In August 2019, just 2 years after Oumuamua's departure, a Crimean amateur astronomer named Gennady Borisov discovered another interstellar visitor. Like its predecessor, this object was traveling on a hyperbolic trajectory, moving far too fast for the Sun's gravity to capture it. Borisov's trajectory indicated it originated from a different region of space, emerging from the direction of Cassiopeia. But unlike Oumuamua, Borisov was immediately recognizable. It looked exactly like a comet. It had a prominent coma, a visible tail, and it was clearly outgassing as solar radiation heated its surface. Spectroscopic analysis revealed it was composed of materials remarkably similar to comets native to our own solar system, primarily water ice, carbon monoxide, and various organic compounds. Fascinating, certainly, but ultimately something we understood. Still, the implications were profound. For all of human history, we'd observed 0 interstellar objects. Then suddenly, in just 2 years, we'd detected 2. What were the odds? The answer, it turns out, is that these objects have probably been passing through our solar system all along. We just didn't have the telescope technology to spot them. And now that we do, we're finding them regularly. Which brings us to July 1st, 2024, when the ATLAS survey system, an automated network of telescopes designed to detect potentially hazardous near-Earth objects, flagged something extraordinary. An object designated 3I Atlas was detected at a distance of 4.5 astronomical units from the Sun. That's about 675 million kilometers, placing it in the region between the orbits of Mars and Jupiter. And here's what made it immediately interesting. It was moving incredibly fast, approaching from a trajectory unlike anything we'd seen before. While Oumuamua and Borisov had approached roughly from the direction our solar system is traveling, meeting us more or less head-on, Atlas was coming in from the side. Like a car running a red light at an intersection, this object was on a perpendicular course. This meant something profound. Atlas originated from a completely different region of the galaxy than the previous 2 visitors. To understand why this matters, we need to think about galactic geography. When we picture the Milky Way, we usually see that classic overhead view. A beautiful spiral galaxy with graceful arms curving out from a bright central bulge. Our solar system sits about halfway between the center and the outer edge. But from our perspective inside the galaxy, we see it edge on. The Milky Way appears as a band of light stretching across the night sky because we're embedded within its disk. Most stars in the galaxy, including our Sun, reside in what's called the thin disk, a relatively flat layer where active star formation occurs and younger stars predominate. Above and below this thin disk exists the thick disk, a more diffused, less dense region populated primarily by older stars. The thick disk represents the galaxy's ancient past. Stars there formed billions of years ago, when the Milky Way was younger and quite different from today. There's less metal content in those stars. In astronomy, any element heavier than hydrogen and helium is called a metal. And the orbits are more chaotic, reflecting the turbulent early days of galactic formation.
Trajectory analysis of 3I Atlas suggests it came from the thick disk region. Initial observations of 3I Atlas revealed something immediately striking. This object is huge.
If true, this object could be extraordinarily old, potentially 7 to 10 billion years old. That would make it older than our entire solar system, which formed about 4.6 billion years ago. This isn't just an interstellar visitor. It's potentially a messenger from the ancient galaxy itself. Initial observations revealed something immediately striking. This object is huge. Early estimates put its overall diameter at around 20 kilometers, though as we've continued observing it, we've refined our understanding. Like Borisov, Atlas has developed a visible coma, that fuzzy cloud of gas and dust surrounding the nucleus. The coma itself measures about 20 kilometers across, but the solid nucleus at the center appears to be roughly 11 kilometers in diameter. To put that in perspective, that's 10 times larger than Oumuamua and 5 times the size of Borisov. These interstellar visitors seem to be getting progressively bigger. Or perhaps we're simply getting better at detecting them, and the larger ones are naturally easier to spot. But size isn't the strangest thing about Atlas. Its trajectory is absolutely remarkable. Because it's approaching from the side rather than head-on, its path will take it past multiple planets. First, it will pass Mars at a distance of approximately 28 million kilometers. Then it will sweep past Venus at about 97 million kilometers. After rounding the Sun, it will pass Jupiter at just 53 million kilometers in March, before exiting the solar system forever. It's like a cosmic grand tour of our planetary system. But here's the curious part. Earth will be on the opposite side of the Sun during Atlas's entire journey through the inner solar system. We'll lose visual contact with the comet as it passes behind the Sun from our perspective, and we won't regain sight of it until December, after it's already made its closest solar approach. From a purely statistical standpoint, this is just an unfortunate alignment. But it hasn't stopped some from speculating about intentional avoidance. A probe designed to survey our planetary system while remaining hidden from the only technologically advanced civilization. Of course, that raises an obvious question. If an alien civilization sent a probe across billions of light years and billions of years of travel time to study our solar system, why would they avoid the one planet showing obvious signs of intelligent life? It seems counterintuitive. Unlike Oumuamua, which we discovered only as it was leaving, we're tracking 3I Atlas on its approach. We have months of observation time ahead of us. Every week it gets closer, brighter, and easier to study. Every telescope on Earth and in orbit is being aimed at this object, gathering spectroscopic data, analyzing its composition, measuring its rotation and outgassing patterns. And unlike Oumuamua, we might actually have a chance to intercept it. We don't have time to design, build, and launch a dedicated mission from Earth. But we have existing spacecraft already in the right neighborhood. Several orbiters around Mars could potentially adjust their trajectories to observe Atlas during its Martian flyby. More ambitiously, NASA's Juno spacecraft, currently orbiting Jupiter, could theoretically depart Jupiter's system and rendezvous with Atlas in deep space during its outbound journey in 2025. These scenarios remain speculative, and the likelihood of approval is low given the cost and risk to existing missions. But the possibility exists, and that's more than we had with Oumuamua.
So let's circle back to our first mysterious visitor. If Oumuamua wasn't an alien spacecraft, and let's be clear, there's zero actual evidence that it was, what was it? The leading scientific hypothesis involves an exotic but entirely natural phenomenon: nitrogen ice. Consider Pluto, that distant world that was demoted from planetary status but remains one of the most fascinating objects in our solar system. Pluto's surface is covered predominantly in nitrogen ice. Nitrogen is the most abundant gas in Earth's atmosphere, 78% of what we breathe. But at the extreme cold temperatures of the outer solar system, nitrogen freezes solid. Frozen nitrogen has an unusual property. It's extremely reflective. This is actually why Pluto appeared large and bright to early astronomers, leading to its initial classification as a planet. In reality, Pluto is tiny, smaller than Earth's moon. But its reflective, icy surface made it appear more substantial than it was. Now imagine a catastrophic impact on a Pluto-like world in another star system. A massive collision shatters the dwarf planet, sending fragments careening through space. One particularly large shard gets ejected from its home system entirely, flung into interstellar space by the complex gravitational dynamics of the impact and subsequent planetary encounters. This nitrogen ice shard drifts through the galaxy for millions of years before chance brings it into our solar system. As it approaches the sun, it begins to warm. The nitrogen ice sublimates, transforming directly from solid to gas, just like comets do with water ice. But here's the key difference. Nitrogen gas is completely invisible. It's colorless, odorless, and doesn't scatter light the way water vapor does. So as the nitrogen sublimes, it creates thrust, real physical propulsion acting like natural rocket engines, but produces no visible coma or tail. To our telescopes, the object appears completely inert even as it's actively outgassing. This explains Oumuamua's acceleration. It explains the lack of visible cometary features. It even explains the high reflectivity. Nitrogen ice is remarkably shiny compared to rocky asteroids. The elongated shape could result from how the object fractured during the original impact, or from differential sublimation, creating an irregular, elongated form over millions of years of travel. Is this what Oumuamua actually was? We can't say for certain without direct sampling, which we'll never get. But it's a hypothesis that fits all the observed data while relying entirely on known physics and naturally occurring materials. No aliens required. We'll learn whether nitrogen ice comets from other star systems are common or rare. We'll gather data on its composition, structure, and behavior that we never got from Oumuamua. We'll understand whether these interstellar visitors are fundamentally similar to objects in our own solar system, or whether they represent exotic compositions born from alien stellar environments. Every interstellar object that passes through our solar system is a free sample from another star system. We didn't have to send a probe trillions of kilometers to collect it. The universe delivered it to us. Each one carries information about its home system, about the processes of planetary formation around other stars, about the composition of protoplanetary disks in different regions of the galaxy. Oumuamua might have been a nitrogen ice fragment from a shattered dwarf planet, or it might have been something even stranger, a type of object we haven't even theorized yet. And when the 4th, 5th, and 10th interstellar objects pass through our solar system in the coming decades, each one will add to our understanding. We're entering an era where interstellar objects are no longer once-in-a-lifetime astronomical events, but regular occurrences that we can study, compare,
and learn from. Think about the scale of what we're discussing here. These objects have traveled for millions or even billions of years through the absolute emptiness of interstellar space. They've witnessed the rise and fall of countless stars, perhaps even the formation of planetary systems. They carry within them the chemical fingerprints of stellar environments vastly different from our own. And now they're passing through our solar system, providing us, a species that only invented the telescope 400 years ago, with the opportunity to study material from other star systems without leaving our own neighborhood. Whether Oumuamua was a nitrogen ice comet or something more exotic, whether 3I Atlas is simply a large ancient comet or holds surprises we haven't yet detected, these questions matter. They matter because every answer we find expands our understanding of how the universe works. We live on one small planet, orbiting an ordinary star in the outer suburbs of a galaxy containing hundreds of billions of stars. These interstellar visitors remind us that we're part of a much larger cosmic story, one where material constantly flows between star systems, where objects born around distant suns can visit our own, where the galaxy is far more dynamic and interconnected than we once imagined.
The ancient universe is literally passing through our solar system right now. And for the first time in human history, we have the technology to watch.